Welcome to another deep dive. Today we're really cutting through the noise around machine learning. It's a field that's, well, it's not just buzz, is it? It's genuinely reshaping things.
Absolutely. Industries, our daily lives, it's
Hmm.
everywhere now.
Right. And our mission here is to take the sources you've shared, sort of unpack the fundamental concepts,
hmm
and really pull out those key nuggets of knowledge that help you, the listener, navigate this complex world with, a bit more confidence.
Yeah, getting a solid handle on the basics.
Exactly. Whether it's for work or maybe you're just curious, you're definitely in the right place.
Good stuff.
So, okay, let's peel back the layers of machine learning. What fundamentally sets it apart from, well, the way we've always told computers what to do?
Well, it's a huge shift, really. Traditional programming for decades meant developers like us writing explicit, static rules, step-by-step instructions for everything.
Like the super detailed recipe for every possible situation.
Precisely. Think of giving a robot an instruction manual for every single task. If
Right.
this happens, do exactly that.
So, my old spam filter example, I'd literally have to code. If email contains free money, classify as spam. I'm listing bad words.
Exactly that. Hand coding every keyword, every suspicious phrase. But machine learning, it just flips that whole idea on its head.
How so?
Instead of us programming the rules, ML lets computers learn from data. They identify the patterns without needing explicit instructions for every single case.
Okay, so back to the spam filter.
Right. An ML approach would feed the algorithm a massive data set. Tons of emails, already labeled spam or not spam.
Ah, so it sees examples.
It sees examples and it infers the characteristics of spam. It learns what spam looks like from the data itself. And it gets better over time. It's this profound shift from telling the computer what to do to letting it learn how to do it.
That difference between telling and learning feels crucial. But learning, it still sounds a bit like magic. What's actually happening under the hood?
Hmm.
What are the steps? It's not like there's a little brain inside, right?
Right. Huh. No, not a biological brain. But there's a clear logical process. It's actually quite elegant. A machine learning model typically goes through three main steps, iteratively.
Okay.
First is the decision process. The algorithm takes input data like your house features and uses its current knowledge to make a prediction. Maybe it guesses the price. It's like its first hypothesis.
But its best guess at that moment.
Exactly. Then step two, the error function. This is critical. It measures how wrong that prediction was by comparing it to the known true answer, if you have one.
So it calculates the mistake.
Precisely. It quantifies the error. Think of it like a scorekeeper saying, nope, you were off by this much.
And the goal is always to get that error smaller, I assume.
That's the driving force, yeah. Which leads to step three, the model optimization process. Based on that error score, the model adjusts its internal parameters,
Awaits.
often called weights, yes. These are like dials the model can turn to change how much importance it gives to different inputs. It adjusts them, makes another prediction, checks the error, adjusts again.
Over and over.
Over and over. It's iterative. It keeps fine-tuning those weights to minimize the error. And that raises the question, how does it know it's improving? Well, that error function and the optimization process are its guide.
That iterative cycle makes sense. And like people, machines don't just learn one way. You mentioned there are different styles, supervised and unsupervised.
That's right. Two major paradigms. Supervised learning is probably the most common. Think of it like learning with a teacher.
Okay.
You train the model on labeled data. That means for every input, you also provide the correct output. The model learns to map the inputs to those known outputs.
Like flashcards. Question on one side, answer on the other.
That's a great analogy, actually. So predicting house prices, you'd give it data on house size, location, number of bedrooms, and the actual prices those houses sold for. It learns the connection.
Got it. And unsupervised. No teacher this time.
Exactly. Unsupervised learning is more like exploring. The model gets unlabeled data, just the inputs, no answers provided. Its job is to find hidden structures or patterns within that data on its own.
So no answer key, just raw information.
Yeah,
That sounds potentially more powerful. It could find things we didn't expect.
it definitely can. It might uncover patterns or groupings we weren't aware of, but as you might guess, evaluating it can be trickier.
Because there's no right answer to check against.
Precisely. A classic example is customer segmentation. You feed an unsupervised model customer purchase data, what they bought, when, how much, and it might group them into segments like loyal high spenders or occasional bargain hunters.
Without you telling it those categories exist beforehand.
Correct. It discovers those groupings based purely on similarities in the data. Success is often judged by how useful or insightful those discovered patterns are.
Fascinating. These two approaches really open up a lot of possibilities. But, you know, even the best learning method needs good material. How critical is the data itself? And how do we make sure the model isn't just good on paper, but actually works in the real world?
Oh, data is everything. Garbage in, garbage out, as they say. It's quality, it's preparation. It's absolutely fundamental. And one of the most crucial steps here is data splitting.
Splitting. Why not just feed it all the data you have? More data, more learning, right?
That seems logical, but it leads to a major pitfall. We split the data, typically into a training set and a test set, precisely because we want the model to generalize.
Generalize, meaning work on new stuff it hasn't seen.
Exactly. The model learns the patterns from the training set, but the test set, that's held back. It's unseen data. We use it at the end to check if the model can apply what it learned to new, unfamiliar examples.
So it's like a final exam.
Kind of, yeah. It prevents the model from just memorizing the training data, including all its noise and quirks. If it only memorizes, we call that overfitting.
Overfitting, I've heard that term. It sounds bad, like it learned too well.
It learned the training data, too, specifically, yes. It fits the noise, not just the underlying signal, so it might look brilliant on the data it trained on.
But then it falls apart on new data.
Completely. It fails to generalize. It's like knowing the answers to only one specific test but being unable to solve any other problem. It's a very common issue.
Okay, so if overfitting is the enemy, how do we fight it? How do we encourage generalization?
Several ways. You can sometimes simplify the model, make it less complex so it's harder for it to memorize noise. There are techniques like regularization, which essentially penalize complexity.
Right.
Getting more diverse training data often helps too. And another powerful technique is cross-validation, where you cleverly rotate parts of your data between training and testing roles to get a more reliable performance estimate.
So it's about checks and balances.
It really is. It's all about building models that are genuinely useful in the real world, not just good at recalling the answers they were already shown.
Building useful models. I like that. Okay, let's get into some specifics. What are some of the actual tools, the algorithms in this ML toolkit?
Sure. A really fundamental one, especially in supervised learning, is linear regression.
Okay, linear regression. What's that for?
It's used when you want to predict a continuous numerical value. Think predicting house prices or temperatures or sales figures.
Things on a scale, not categories.
Exactly. It works by modeling a linear relationship, basically, trying to find the best fitting straight line between your input features, like house size, and the target variable, the price.
Simple, but probably quite powerful for the right problems.
Very powerful, and often a great starting point. Now, besides the algorithms, how you prepare the data for the algorithm is also key. We touched on data quality, but there are specific techniques like feature engineering and feature selection.
Feature engineering and feature selection. They sound related.
They are, but they're distinct. Feature engineering is, well, it's almost an art form within data science. It's where you create new features from the existing ones or transform them to make them more informative for the model.
Can you give an example?
Sure. Say you have data with someone's height and weight. You might engineer a new feature, their body mass index, BMI, calculated from height and weight. That single BMI feature might be more predictive for certain health outcomes than height or weight alone.
Ah, so you're crafting better ingredients for the model.
That's a good way to put it. Then there's feature selection. This isn't about creating new features, but about choosing the best subset of the features you already have.
Why would you not use all the features?
Sometimes less is more. Some features might be irrelevant, just noise. Others might be highly correlated with each other, providing redundant information, which can confuse the model or make it less stable. Feature selection aims to pick only the most impactful, relevant features.
So engineering makes new things. Selection picks the best existing things.
Precisely. Both are crucial for boosting accuracy, simplifying models, and reducing that risk of overfitting we talked about. Often, good feature work makes more difference than tweaking the algorithm itself. It needs that human insight.
That makes a lot of sense. Okay, so we've built a model, maybe using linear regression. We've engineered features. But how do we really know if it's any good? And especially for classification, telling spam from not spam, or detecting disease. You mentioned accuracy isn't always enough.
Right. For classification, accuracy can be deceptive. We need a deeper look, and the workhorse for that is the confusion matrix.
The confusion matrix sounds aptly named. What does it show us?
It's basically a table. It lays out exactly how your model performed by comparing its predictions to the actual true outcomes. It breaks it down into 4 key categories.
Okay, what are they?
You have true positives, TP, The model correctly said yes when it was yes.
Yeah.
Correctly identified spam. True negatives, TP. Correctly said no when it was no. Correctly identified important email as not spam.
Good.
Then the errors. False positives, FP. The model said yes, but it was actually no. Your important email mistakenly flagged as spam. A false alarm. Also called a type-by error.
Okay, annoying.
And false negatives, FN. The model said no, but it was actually yes. A spam email slipping into your main inbox. A miss. Type 2 error.
Right, so it maps out all the ways the model can be right or wrong.
Exactly. And from those four numbers, TT, TN, FP, FN, we can calculate much more useful metrics than just overall accuracy.
Like what? What else should we look at?
Well, there's precision. That's asking. Of all the times the model predicted yes, spam, how often was it actually correct? It measures the reliability of positive predictions. TP plus FP.
Okay, high precision means fewer false alarms.
Correct. Then there's recall, sometimes called sensitivity. That asks, of all the actual yes cases, all the real spam, how many did the model correctly identify? It measures how well the model finds all the positive instances. TP plus FN.
So high recall means fewer misses.
Precisely. And often there's a trade-off between precision and recall. Improving one might lower the other.
So which one matters more?
It depends entirely on the context. Is it worse to miss a spam email, low recall, or to accidentally flag an important email as spam, low precision? The answer drives which metric you prioritize.
I see. Any other key metrics from the matrix?
Yes, the F1 score. It's the harmonic mean of precision and recall. It gives you a single number that balances both, and it's especially useful when you have imbalanced data like way more non-spam than spam emails, where accuracy alone would be misleading.
So the confusion matrix and these metrics give a much richer picture of performance.
A much more nuanced understanding, definitely. Vital for real-world decision-making.
Fantastic. Now, we started by contrasting supervised and unsupervised learning. Let's loop back to unsupervised with a concrete example you mentioned. K-means clustering. How does that work?
Right. K-means is a classic unsupervised algorithm. Its goal is simple. Take a bunch of data points and group them into K distinct clusters, where K is a number you usually specify beforehand.
And it does this without labels.
Without any labels. It just looks at the features of the data points. The means in K-means refers to the centroids, the center point of each cluster. The algorithm tries to place these K-centroids and assign each data point to the nearest centroid such that the distance within each cluster is minimized.
So it wants tight, compact clusters.
Exactly. It iteratively adjusts the centroid locations and the assignments of points to clusters until things stabilize, until the clusters are as distinct and internally similar as possible based on the data's features.
And this works on numerical data usually.
Typically, yes. Unlabeled numerical data. Think back to customer segmentation based on purchase history amounts, frequency, things like that. K-means could find, say, 3 or 4 distinct groups of customers based on those numbers.
Discovering hidden structures in the numbers.
It's the essence of it. Discovering inherent groupings you might not have known were there.
Wow. We've covered a lot of ground. From that fundamental shift away from traditional programming.
Right. The move to learning from data.
To the 3 steps models use. Decision, error, optimization.
That iterative learning cycle.
And the big learning styles. Supervised with its labels, unsupervised finding hidden patterns.
Teacher versus explorer.
The absolute necessity of good data, splitting it, and avoiding that overfitting trap.
Can't stress that enough. Data prep and validation are key.
Specific tools like linear regression for prediction and K-means for clustering.
And feature engineering and selection to help them work better.
And finally, really understanding performance beyond just accuracy with the confusion matrix, precision, recall.
Getting that nuanced view, it's crucial.
We really hope this deep dive would give you, our listener, a shortcut to feeling more informed about these core ML ideas. Not just the what, but the why and, how it actually works.
Yeah, hopefully demystifying it a bit.
So wrapping up, what does this all mean for you?
Well, here's something to think about. As you see more and more AI machine learning in your daily life, whether it's recommendation engines, maybe medical diagnostics, financial tools, how does understanding these basic principles, how models learn, how they're optimized, how they're evaluated, how might that change the way you interact with these systems?
Or even how you question them.
Exactly. How you interpret the results, or maybe even challenge the assumptions behind them. Knowing a bit about the how can really shift your perspective on the what.
A really powerful thought to leave us with. Thank you for joining us on this deep dive into machine learning. We hope you feel a little more informed and definitely a lot more curious.